So hello everyone, welcome back to our YouTube channel. In this video, I'm going to discuss about magnetic materials. What are magnets? What are the different properties of magnets? And what's the reason behind magnetism? So all these things I'm going to discuss in this video. So let's get started. So first of all, what are magnets? So as we have been using magnets in our daily life, so we know what are magnets, the materials which produce magnetic field. So if you have any material and the material is producing a disturbance around it. That disturbance is known as magnetic field. So any material which produce a magnetic field, or you can say disturbance around it, that materials we call them as magnets. So what's the reason behind this magnetism? So the reason behind this magnetism is electron, the motion of electron. So motion of electron. So as we know, we have two types of motion. First one is spin, where electron moves on its own axis. And second one is orbital motion of electron, where electron is moving in a particular orbit around the nucleus. So because of these two motion, we have that disturbance around the material, which is known as the magnetic field. So like this, electrons plays very important role to have the magnetism, to have the property of a magnet. So further, what is magnetic moment? So to understand magnetic moment, uh, first you should understand what is magnetic dipole. Magnetic dipole. So, as I said, electron is moving, right? And because of this movement, it is creating the disturbance. So, the electron itself is acting as a tiny magnet. So, that tiny magnet is known as a magnetic dipole. Magnetic dipole. So, this tiny magnet is known as a magnetic dipole. And magnetic moment, this tells us the strength and direction. So, magnetic moment tells us the strength and the direction of this magnetic dipole. The strength of the magnetic dipole and the direction of the magnetic dipole is given by magnetic moment. So it tells us how strong and in what direction the magnetic source is. So as I told you, electron is spinning, it is revolving, and it is behaving as a tiny magnet. And that tiny magnet is known as a magnetic dipole. And the strength of this magnetic dipole and the direction of the magnetic dipole is given by magnetic moment. So this is nothing but a magnetic moment. So because of moment, we have magnetic dipole, and the strength of that magnetic dipole is given by magnetic moment. So I hope you have understood so far. Further, we have domain and domain walls. So what is domain? So domain is nothing but a region. It is a region where magnetic dipoles are arranged in a particular direction. So you can see this one is the region, this small region. In this region, magnetic dipole is in this direction. So this complete region is known as domain. So where all the magnetic dipole are arranged in a particular direction. And what are domain walls? So you can see here this magnetic moment or magnetic dipole in this in this direction, and in this domain, magnetic dipole is in this direction. And in between there is one line. That line is known as magnetic domain. So magnetic wall separates the different direction of magnetic dipole. So it separates the different direction of magnetic dipole. So direction of in this region, dipole direction is in this, and in this region, magnetic dipole direction is in this direction. So it separates these two directions. So the between this wall is known as domain wall. So I have listed some more pictures related to this. So you can see this is the domain. This all regions are domains where millions of atoms magnetic dipole is arranged in a particular direction. And this region which separates the dipole direction, this is known as domain wall. So this is one picture from a magnetic force microscope, which is used to see these domains and domain wall. So this black region is domain wall, and this white region which is present in between is known as domain. So these two terms are also very important to understand the magnets. So magnetic dipole. So these are magnetic dipole, and these are arranged in a particular direction. That region is known as the domain, and the wall which separates two different direction of magnetic dipole is known as domain wall. So that's it. Further, yeah, these are the different magnetic properties. First one is magnetic field. So let me give you one example. So for example, this is our magnet or material, let's say magnetic material, and this magnetic material is surrounded with a coil. And in this coil, I have just given a current, and because of this current, we know magnetic field is going to generate. That magnetic field is known as H, which is external magnetic field. External magnetic, sorry, uh, external magnetic field. So because of this current, electrons are going to move, and because of that electron, we are going to get this external magnetic field. So this external magnetic field causes magnetic material to become magnetized. To become magnetized. So this is the magnetic field, which is represented by H. So external magnetic field or magnetic field, and this magnetic field causes the magnetic material to become magnetized. So that's the magnetic field. Further, we have magnetic flux and magnetization. So because of this external magnetic field, what's going to happen inside the material? The dipoles which are present inside the material, they will arrange themselves in a particular direction. And because of this arrangement, they are going to produce their own magnetic field. That magnetic field is known as magnetization, which has a formula magnetic moment per unit volume. Or you can remember it like this, that because of this external magnetic field, this magnetic dipoles are going to arrange and they will create their own magnetic field. That magnetic field is known as magnetization. Or you can say how strongly a material can magnetize. That thing in the presence of external magnetic field is given by magnetization. How strongly a material can magnetize in the presence of external magnetic field is given by magnetization. Or you can say due to presence of this external magnetic field, dipoles are arranged in a particular direction and they produce their own magnetic field. That magnetic field is known as magnetization. So that's the simple definition of magnetization. And next term is magnetic flux. So what is magnetic flux? I have to clear this slide. Yeah. So magnetic flux is B dot A, where B is total magnetic field. Total magnetic field, which is the combination of B internal plus B external. As I told you, B external is nothing but H, which is external magnetic field, and B internal is magnetization, which is coming due to the magnetic dipole arrangement. And these two are B dot A, so it's a dot product. If you open the dot product, you will get B A cos theta. So flux tells us how much magnetic field is passing through an area. So if we have an area, how much magnetic field passing through this. So this thing is given by magnetic flux. Then we have saturation magnetization. It's nothing but maximum magnetization. Maximum magnetization. Maximum magnetization is nothing but saturation magnetization. Maximum value of magnetization. And then we have these two terms. These two terms are very important. First one is retentivity and second one is cohesivity. So cohesivity, for example, I have one this diagram. Yeah. In this diagram, this is the magnetic material which is present in the absence of external magnetic field. So when I apply the external magnetic field around it, you can see these domains arrange themselves in a particular direction. Now, the amount of reverse magnetic field which I require to make this material back to zero magnetization, or you can say back to normal material. That amount of reverse magnetization or reverse external magnetic field is nothing but cohesivity. So it's like amount of reverse external field. So it's the amount of reverse external field required to make the material back to zero. So this is the normal material. So this is the normal material. I've applied the external magnetic field and this material gets magnetized. Now I have to get this material back to its normal position, or you can say normal state. For that, how much amount of external magnetic field required, that thing is given by coercivity. That thing is given by coercivity. And last term is retentivity. Retentivity, the name itself is saying that retention. So if I remove this external magnetic field, so this magnetic dipole will try to get themselves into their natural state, but some of them will still arrange themselves in that direction only. So this residual magnetization is nothing but retentivity. How much material, or you can say how much magnetization is remain in the material when we remove the external magnetic field. That is nothing but retentivity. And last term is susceptibility, magnetic susceptibility, which tells that how easy to magnetize the material. So that is the magnetic susceptibility. So these magnetic properties are very important. So thank you so much. In upcoming video, I'm going to discuss about neodymium iron boron magnet, which is a very strong magnet. And stay tuned. See you in the next video. Thank you for watching.